In this example, we want to find the surface integral of x plus z ds, where s is the surface and the first octant of the portion of y squared plus z squared equals 9 between x equals 0 and x equals 4. Now I'm going to actually choose to compute this surface integral by, instead of using a function to represent this surface, I'm going to turn it into a parametric parameterization of it using a vector valued function. And the reason I'm going to do that, if you want to take a look at this example in the book, they do it in as a function. And what you'll notice is when you take that f sub y, when you take the derivative with respect to y, you get something that is undefined at y equals 0 because you end up with a square root of 9 minus y squared in a denominator, which would mean that when we take our integral, we would have to do an indeterminate, or improper, integral. So we would have to do a limit rather than, this is going to help us avoid a limit. So let me sketch that surface for us really quick. So this is a cylinder in the YZ plane. It's all concentric circles with radius of 3, and then it runs parallel to the XZ plane, or sorry, the x-axis. So we've got this cylinder is what we're looking at. And then all we want of it is the first octant portion between x equals 0 and x equals 4. So basically we're going to have this semicircular arc, and then that's going to extend down. It's going to extend over to here and then arc down. So we're just looking for this portion of it here. So this is the issue we would have with, like I said, like leaving it in terms of a function, is we would have to integrate to y equals 3. We'd have to have 3 on a y integral bound, and it would end up being an improper integral when we set it up. So what I'm going to see instead is, notice this is a surface of revolution. So instead I want to try and set it up as being revolved around the x-axis. And as a surface of revolution, it's actually a very simple surface of revolution where all we're doing is rotating a line. So we're just rotating the line y equals 3 about the x-axis. So what that's going to let us do is let this r of uv, well, we can let x be our parameter u, and then y is going to be the radius, which is 3. So it doesn't need to be a function radius, it can just be a constant. And then that'll be cosine of, we could do a v, and then we'll have 3 sine v for the z component. And so what we can do now is look for like that r sub u and that r sub v, those partial derivatives. So we're going to end up with 1, and then we'll get negative 3, or actually, just kidding, we're doing the partial derivative in terms of u right now. So then the second 2 in terms of u are just going to be 0, 0. And then in terms of v, we're going to get 0, and then the negative 3 sine v, and then we'll get 3 cosine v. So then if we're remembering to do that surface area portion, we need the cross product of that. So then we set up our cross product with ijk, and then 1, 0, 0, and then 0, negative 3 sine v, and then 3 cosine v. And when we set this up, we're going to take first the I component, which we'll notice we're going to have 0 times 3 cosine v minus 0. So really the I component is 0. And then we'll have minus for j. We're going to end up with 1 times 3 cosine v. And then that's just going to end up being minus 0. And then we'll have plus for k. We're going to get negative 3 sine v. And then it would be minus 0. So we get negative 3 cosine Vj plus, or really minus, 3 sine Vk. So we can take that magnitude of that cross product. So we'll have the square root. We're going to end up with 9 cosine squared V plus 9 sine squared V, which is just going to end up being the square root of 9. When we factor that 9 out, the cosine squared V plus sine squared V is 1. So my magnitude is just 3. Up top, I forgot, I should have done it right when I did it. We came up with this parameterization. We should also come up with our bounds for U and for V. U is really the X component, so we need it to range as far as X does, so that was from 0 to 4. And then V is really thought of as the angle that's kind of swinging this up and around the X-axis. So it's going to start at 0, and then because we let Y be cosine and Z be sine, so we're in this orientation, so this would be the 0 point for our angle, and then we're going to swing up to 90 degrees or pi over 2 radians. So then putting all this in our integral, we'll get the integral of S of, we had x plus z ds was the original one we're trying to do. This is now going to be a uv integral. So u ranges from 0 to 4, and v is from 0 to pi over 2. And we need to do x of uv plus z of uv. So we need to replace those with the components that we came up with up top. And then we multiply that by that magnitude of the cross product of r sub u crossed with r sub v. And we're doing this du dv. So up top what we saw was the x component is u, and then the z component is 3 sine v. So we're going to end up with the double integral, 0, 4 on the inside, 0 to pi over 2 on the outside. We'll have u plus 3 sine v, all times that magnitude was just 3. So then this is du dv. So then we're going to end up with the integral 0 to pi over 2 of 3 times u. When we integrate, we'll go to u squared over 2, and then we're going to get plus 3 sine v is all a constant, so then it's just going to be times u. We'll evaluate that from 0 to 4. So then we're going to get the integral 0 to pi over 2. We'll get 3 times 16 over 2 is just going to be 8. And then we'll have plus 3 times 4 is 12 sine v. And this is dv. So we're going to get 3 times 8 is 24. So we'll have 24 times v, and then we're going to have plus 36. Sine v is going to go to negative cosine v, and we're going to evaluate this whole thing from 0 to pi over 2. So plugging in pi over 2, 24 times pi over 2 is going to be 12 pi, and then we're going to have plus 36 times negative cosine of pi over 2, but cosine of pi over 2 is 0. And then we'll get minus 24 times 0 is 0, and then we'll get negative 36 times cosine v, which is 1, so minus 36 times 1. So all in all, this is a 0, and there's another 0. We end up with 12 pi plus 36. So our integral ended up just being a little bit easier by converting it into a parametrized version of that curve rather than leaving it in function notation. Like I said, if you want to see how it works leaving it in function notation, you can go ahead and read that example. It is done in the textbook in this section, which is more in that section 15.6 still.